Good morning and welcome to this next lecture on vibrations of plates and shells. So, last time we were doing or deriving the Euler Bernoulli beam equation using Hamilton's law, and in particular I was doing it in the way that Sodel does in the book. Okay, he uses or keeps the stress and strain terms that are relevant and does not impose the shear strain zero condition in the beginning. So he continues with this displacement profile without specifying what beta is. Okay, and applies the variational principle. Okay, so now we went quite a bit last time, so we are over here. So the potential energy has all these terms. So if for the moment we'll ignore the boundary terms, okay, we'll just stick with the integral terms. So let us see what we have. Nxx delta u b dx, Nxx b dx delta u integral 0 to L with a minus, and then we have okay, minus del mxx delta x b dx delta beta integral 0 to L, and qxz delta beta b dx plus qxz b dx delta beta, and then delta w, okay, minus integral 0 to L del qxz del x b dx delta w. This is the delta u term. Okay, now this, okay, this is delta u term. Now there will be an integral on that, time integral on that, delta u dt. That's one part. Now the kinetic energy part, okay, so the kinetic energy we will now consider, let's say there is every point as a vertical velocity w dot and a horizontal velocity u dot. Okay, now we are doing pure bending here, pure bending. That means the axial displacement u is equal to z beta. Okay, there is no mean axial displacement of the neutral axis. okay, that is what is pure bending. So u dot is z beta dot, okay. So if I take my kinetic energy to be 1/2 rho velocity vector dot okay, and then the element dx dy dz, okay, and integrated minus h by 2 to h by 2 integral 0 to b integral 0 to L, okay. So now if I say that my velocity, I am sorry, this is just velocity, okay. I say that my velocity is equal to u dot I plus w dot k, okay, then v dot v is equal to u dot square plus w dot square, which is equal to z square beta dot square plus w dot square. So now my kinetic energy is 1/2 integral minus h by 2 to h by 2 integral 0 to b integral 0 to L rho z square del beta del t whole square plus del w del t whole squared dx dy dz, okay. We will do the h and b integral, okay. So what that gives me, I just straight away do it, integral 0 to L rho I del beta by del t whole squared plus rho a del w by del t whole squared. Dx. This is of the form bh cube by 12. This is bh. This is the area. Okay. Now the variation of this thing, okay, is given by integral 0 to L rho I beta dot delta beta dot plus rho a w dot delta w dot dx, okay. Now we have to do the combination. The law says integral t1 to t2 delta of u minus t or t minus u okay dt must be equal to 0. We will take delta t to one more step. We will say delta t is integral 0 to L, okay. I transfer the derivative to this, I transfer the derivative to this, and there will be boundary terms. Okay, let us do it. Okay, so we will get, let us see, let me do a combination first. Let me do a combination first. So we have integral t1 to t2 integral 0 to L rho I beta dot delta beta dot plus rho A W dot delta W dot dx. Okay. So that if I take to the next page, integral t1 to t2 delta t dt, I am just rewriting t1 to t2 integral 0 to L rho I beta dot delta beta dot plus rho A W dot delta W dot dx dt. Dx and dt. Okay. So here we will do the time integral first. If we do that, we get integral 0 to L rho I beta dot delta beta t1 to t2 minus integral t1 to t2 rho I beta double dot delta beta dt plus rho A W dot delta W t1 to t2 minus integral t1 to t2 rho A W double dot delta W dt dx. Now Hamilton's law says that between two known states, at t1 and t2, so all variations at these two endpoints are 0. So delta beta is 0 at t1 and t2, delta W is 0 at t1 and t2. Okay. So we are left with integral 0 to L integral t1 to t2, put a minus here, rho I beta double dot delta beta plus rho A W double dot delta W dt dx. Okay. Now we will combine both. Okay. So I ignore the boundary terms in the space also, and here the boundary terms went to 0. Okay, so I will combine the, okay, so I have T1 to T2 delta of u minus t dt, okay, that can be written as integral 0 to L integral T1 to T2. The sign changes here, rho I beta double dot delta beta plus rho A w double dot delta w plus minus delta u nxx del nxx by del x minus delta beta del mxx by del x plus qxz delta beta minus delta w del qxz by del x b into dt into dx. Okay, now what do we have for delta beta? We have integral 0 to L integral T1 to T2 rho I beta double dot by B. This is delta beta, this is delta beta, and that is delta beta. Okay, then minus del mxx by del x plus qxz. Okay, then dt b dx. What do we have for delta u? We have integral 0 to L integral T1 to T2 delta u, only this term. So we have del minus del n xx by del x. Okay, had we included the axial inertial term, we would have axial inertia. We didn't do that, okay, because we were not interested. Okay, dt b dx. Then we have, so this is done, this is done, this is done, this is done, and then we have delta w, which is integral 0 to L integral T1 to T2 rho A w double dot by B minus del q x z by del x dt b dx. Okay, so this entire thing must be 0. This entire thing must be 0, and for any manner that these variations happen, any form of these variations, and therefore the coefficient of each of these must be 0. Okay, so one is this must be 0. Okay, so let's see, I have del mxx by del x minus qxz is equal to rho I beta double dot by b. This is the rotational inertia term. and therefore in the Euler-Bernoulli theory we ignore this. This is ignored in Euler-Bernoulli theory. Okay, so del mxx del x is equal to qxz. That's one thing. Of course, the other is the axial term. We don't worry about it. And the delta w term says that del qxz by del x is equal to rho a w double dot by b. Okay, or if we substitute qx as del mxx del x, this is equal to del 2 mxx del x square. Okay, so far we have not brought in the fact that shear strain is 0. We have not brought in this fact so far. Okay, so now what do we have? My u is equal to z beta. This we have brought in, so that my axial strain is z times del beta by del x. Okay, and then what is my shear strain? That is equal to del u del z plus del w by del x is equal to beta plus del w by del x. Here for the first time we set shear strain to 0. That gives me beta is equal to minus del w by del x, which means my epsilon xx is equal to minus z del 2 w del x square, which means my sigma xx based on Euler-Bernoulli theory is minus Ez del 2 w by del x square. Okay, which means my moment resultant is equal to integral minus h by 2 to h by 2 E epsilon xx z dz. Okay, sigma xx z dz, which is equal to integral minus h by 2 to h by 2 E z square del 2 w by del x square dz, which gives me minus E I by b del 2 w by del x square. Okay, now if I use this definition, so del 2 mxs is minus ei del 4 w del x 4, that is equal to rho a w double dot, and therefore we have ei del 4 w del x 4 plus rho a w double dot is 0. Okay, this I is bh cube by 12 and this A is bh, area of the cross section. Okay. So what I wanted to show by this example, by this previous example, is how Hamilton's law is applied in the book. Okay. All relevant stresses and strains are used in the strain energy expression. Okay. Then in the process, the z or alpha 3 integral minus h by 2 to h by 2 integral is done. That gives the force moment resultants. Force moment resultants. Like nxx and mxx, these are force per unit length and moment per unit length. They have such units. They are not full moment and full force units, okay, but they appear. The moment you do this z or alpha 3 z direction, or in our general case alpha 3 direction integral, okay, and then rotational inertia is ignored. Rotational inertia is ignored from the kinetic energy term. And then towards the end, the shear strain is 0 condition. Shear strain 0 condition is used. Okay. So you can see that even though the shear strain is 0, the integrated effect of sigma xz, which is qxz, is not equal to 0. Okay. So that is the inconsistency. Okay. We finally had qxz, which is integrated form of shear strain, but what we are saying it epsilon xz is equal to 0. Okay. So this is what will be followed in the general alpha 1, alpha 2, alpha 3 coordinates for a curved shell. For a curved shell. Okay, in the derivations to follow. Okay. So we'll close the lecture here. We'll continue from here next class. Thank you.